Now that we have an understanding of voltage, current, and resistance, we can get into something known as Ohm's Law. We're also going to look at electric power and shorts or short circuits in this video. All right, let's jump right in. Ohm's Law, part A of our notes. Ohm's Law is really just an equation, and it's describing or it's relating the three terms that we've already learned in previous videos: current, voltage, and resistance. Here is the equation right here. This itself is Ohm's Law. All right, it says that the current that flows through a circuit is equal to the voltage that's being supplied by like a battery divided by the resistance. Now, this equation, you don't need to know where it comes from, but it should hopefully make sense to us. Voltage, remember, that has to do with the energy each unit of charge is given. It makes sense that voltage is in the numerator, because if you have more and more voltage, that means you have more and more energy for those charges. It makes sense then that those charges are able to kind of move faster, to have more electric current. It also hopefully makes sense that resistance is in the denominator, because remember, resistance impedes the flow of charge. So if you have more and more resistance, even think of, again, like our river example. If you have more and more stuff clogging up that river, the flow of water is going to go down. So as resistance increases, the current decreases. Okay, this is usually how I write it. This is what you're going to see on the AP equation sheet. It's the exact same equation. They've included this uppercase Greek letter delta. Recall that means change in. All right, I often leave that out. Remember, just like for gravitational potential energy, and I use that example of like dropping a ball off a cliff in our prior video, voltage is really all about a change in energy. What I mean is the battery, if you recall, gives energy to those charges. It gives them 9 volts, or it gives 9 joules per coulomb of charge. So as those electrons go from here to here, or from here to here, they are given 9 volts. They increase their voltage. When they go across the light bulb, they decrease. There's a change in their voltage. You're going to see that when we measure voltage, we're actually always measuring by comparing two locations. All right, that'll make more sense a little later. So that's why they have that delta sign in. Don't worry about that. Okay, don't let that confuse you when you see it on the AP equation sheet. This equation is also rewritten in this form. It's the exact same equation. I've just moved that voltage off to one side. This is maybe helpful if you want to graph something, because this looks very similar to our slope-intercept equation from algebra, y equals mx, or y equals mx plus b. You will often see it written this way. It's the same equation, same terms as before, all the same units. Now, with all that said, Ohm's law historically wasn't written in any of these three ways, or any of these two ways, really. George Ohm, who was a scientist in the late 1700s, was really studying the resistance, what he called the resistance of materials, like this light bulb. This light bulb offers some resistance in the circuit. And what he really figured out, the origin of Ohm's law, is that the resistance, what a light bulb, for example, does, is there's a ratio between the voltage and the current. And that ratio is this, V over I. And what George Ohm mostly found was that the resistances of objects is constant, meaning that ratio V over I is constant. And again, that should make sense, because if I increase the voltage of what's going across this light bulb, there's going to be more current, all right, or vice versa. So this is really what George Ohm came across, that the resistance is based on this ratio between voltage and current, and he found that that ratio, or R, is a constant value. Now, we're going to make things a little more confusing, because Ohm's law isn't really a set law. Some things follow Ohm's law, but not everything. There are instances where R, or this ratio, is not constant. For example, increasing the temperature of material can sometimes change R. Sometimes the material themselves have different R values. If a material does obey Ohm's law, meaning it has a constant resistance, if this light bulb has a constant R, even if I change V or even if I change I, we say that that object is ohmic. All right, kind of a funny word to say, ohmic. It obeys Ohm's law. If that object does not have this constant ratio, or if R is not staying constant, we say it's not, or it's non-ohmic. Okay, now for this class, unless it says otherwise, we'll assume that circuits and material obey Ohm's law. Okay, we're going to use this equation in quite a bit in future applications of circuits. So unless it explicitly says otherwise, we'll assume that we can use this Ohm's law, this V equals IR, or this I equals V over R. But just know sometimes materials do not follow it. It just means that the R is not staying constant, the resistance. Okay, that's Ohm's law. Part B. Part B, we're talking about electric power, and we've already seen the term power before, and the basic definition is staying the same. Power is how much energy you are putting out or using up in a given amount of time. If you are much more powerful than your friend, it probably means you're putting out more energy or you're doing more work in a given amount of time. It's really the same thing for circuits. All right, the power of a light bulb, it's still all about how much energy it's putting out in a given unit of time. The equation for power is I times V. Again, this is what you'll see on the AP equation sheet. Again, they have that delta term. Don't let that confuse you. I'll often just write it as I times V. It's based on the current and the voltage. Now, everything else is staying the same. The units for power, just like before, are watts. W-A-T-T-S. When you buy a light bulb in a store, if you've ever done that, all right, light bulbs are rated by their wattage, how much power, how much electricity they're pumping out. Okay, so this equation is on the AP equation sheet. Like I said, you don't need to know where it comes from, but like before when we studied power, there's a few different ways we could actually rewrite the equation based on the fact that we just learned about Ohm's law. And here's what I mean. We know that power equals IV. But from Ohm's law, V equals IR. So instead of this V term right here, I could plug in I times R, and I get this equation. Power equals I squared times R. It's the same thing, still finding the power of an object just by using different terms. Or I could look at Ohm's law written this way, I equals V over R. So here I have P equals IV. Instead of I could plug in V over R. So when I multiply that out, I get power equals V squared over R. So these three equations, they all should get you the same answer. But this might be helpful if maybe you're told a light bulb, for example, has a constant resistance and there's more current passing through it. From this equation, you know the power must be increasing. So if you don't know one of these two things, I or V, maybe one of these other equations might be helpful. However, these two equations are not on the AP equation sheet. Okay, but this equation is, and Ohm's law, of course, is. There is a helpful tip. If a question asks about the brightness, I've seen a lot of times questions about like, which light bulb is brighter? Okay, brightness, well, that's power. They're asking you in kind of an indirect way to compare the power of those light bulbs. So if you see the term brightness, you're trying to figure out which object, or you're trying to calculate an object's power. All right? The last section is all about short circuits, and you may have heard that term before, short circuits. We're looking at why short circuits are bad. And it's really all about Ohm's law as well as what we saw about energy. So by Ohm's law, we know this, I equals V over R. If we have a simple circuit like this, we have our battery which supplies the voltage, a light bulb, or like a computer processor or a graphics card, all those things resist that current in some way. So I have this light bulb labeled as something that resists current. This is our source of R. Remember, for the most part, wires don't have any resistance. Okay? Well, if we instead had this diagram right here, if there was no light bulb, I just kind of blocked out that light bulb, sorry for my poor drawing. If all I had was my 9-volt battery and I simply connected wires from one end to the other, here I have 0 resistance, or 0 ohms of resistance. Because remember, those wires really don't offer any. Well, maybe you can see how that's going to be a problem. If I have a circuit with 0 resistance, the current approaches infinity. Imagine a circuit where you have an infinite number of electrons flowing every second. That's horrible. I have a computer simulator, my good old FET. Okay, here I have a battery, and I just have the wires, and in this simulator, like our normal assumptions, the wires have no resistance. So if I connect it, oh my gosh, even though this is a pretty small battery, it's just 9 volts right here, with no resistance, the current approaches infinity. Look how fast these electrons are flowing. The electrons would start trying to approach the speed of light in terms of how fast they're moving. So this is very bad. Also, another way to look at it, we just learned about power. If I approaches infinity, you have an infinite amount of power being put out. Those batteries are going to die very, very quickly. Now, this is also a problem when we think of conservation of energy. Remember the whole idea. These batteries give charges an additional amount of energy, and those electrons must give up that energy. Well, if they have to give up that energy and now there's no light bulb, where is that energy going to go? Often it would go back into the battery itself, or if you remember, real wires actually have a small amount of resistance. If you ever in real life take a battery and just connect two wires to it, you're going to start feeling the battery and the wires heat up. Maybe things are going to start melting. You're going to hear things, or you're going to see smoke possibly coming from that circuit, because if there's no resistance, that current and that power approach extremely high levels. That's very bad. All right, a short circuit refers to when you have something like this going on, where you are missing out on resistors. Maybe you design a circuit that looks like this, but by accident, there's actually a wire going like this. And so you're taking a shorter path. You're not going through resistors. That can really mess up your circuit if you wanted to have a very specific amount of current, and now all of a sudden you have much more current than before. Okay, you might have heard this term, electricity takes the path of least resistance, and that's again just kind of talking about this idea of shorts. If I have this set up here, I'm going to go back to this diagram. Now it's almost like the electrons have a choice. They could either go through this resistor, this light bulb, and continue through this outer path, or they could take this inner path. Well, here, the current is going to approach infinity because there's no resistance. Whereas here, there is definitely some amount of resistance, so you're going to have less current. Which path is going to have more electrons flowing through it? It's this shorter path. That's what this means. If there's less resistance by Ohm's law, you're going to have more electrons flowing. That's all that this little statement is saying. Okay, so that's all we need to know about shorts, and then of course Ohm's law and power. Thanks a lot.